All Saturday morning physics events are special, but this one is unique and particularly special because we are celebrating the science of the art of physics professor Jens Zorn, our dear late colleague. 6 of the colleagues from the physics department will be telling you about the science behind 6 sculptures. And I also want to note that usually at the end of Saturday morning physics, we have a Q&A, but we won't today. Instead, and we will write this up here, we invite you to send your questions to physics@umich.edu. Thanks, Monica. Now, I would like to introduce Professor Lou Lee, who is currently the chair of the physics department and a condensed matter physicist.
Thank you, Tim. Welcome. Oh, welcome, yes. So, again, this is such great events. I'm so happy that many of you are able to come in such a lousy weather. But just a few things. Some of you may know, but my colleague Harrietta Eva will step in and become the chair on July 1st. So she's right here. And she will be past speaker. Also, for the audience here, you guys should know both our research very well, because her student Justin, my student Aaron, gave the Saturday morning physics talk in March. So, right, wonderful. So great, without further delay. Now, Eric, please.
Yeah, I'm Eric Zorn. This is Karen Zorn. We're Jens's children. We're honored to be here, and we're grateful that the department is putting on this event. We're going to give you a little background about his long and wonderful and interesting life. We hope we'll provide some context for what you're about to hear today.
Jens was born in Halle, Germany in 1931 to Alice and Max Zorn, who were both mathematicians and both active in the underground movement opposing the rise of Adolf Hitler. Ultimately, they fled to the United States in 1934. Max had a fellowship at Yale and later moved the family to Los Angeles, where he had a professorship at UCLA. When Jens was a teenager, Max was lured to Indiana University in Bloomington, Indiana.
He was a gangly and awkward kid, to hear him tell it, but he found that he could make money and meet cute girls by becoming a photographer.
One of the cute girls he met and photographed was Francie Barnhart, daughter of an IU historian. They married after he finished a stint in the U.S. Navy, and she finished college, and they stayed married for more than 70 years.
Jens was an electronics technician in the Navy and developed a knack for maintaining and fixing delicate instruments. This led to an interest in physics, which led him to pursue graduate studies at Yale University after he was graduated from Miami of Ohio.
Eric was born in New Haven, Connecticut, and I was born here in Ann Arbor 5 years later, shortly after Jens got his PhD.
We're still not exactly sure what he did all those days and nights in the mysterious, cluttered laboratories in the basements and sub-basements of Randall Lab. We're hoping to be enlightened today.
But Jens was always there for us. He was always willing to stop whatever he was doing and help with our homework, dispense advice, and so on. When he would help with our homework, particularly math and science homework, he would often illustrate problems with clever little drawings. This was the very first hint we had that he had an artistic as well as a scientific side.
In 1992, at the age of 61, Jens chanced into a second career as a sculptor. The story goes that after his friend and physics department colleague Arthur Rich died of brain cancer at the age of 52, his family commissioned a New York sculptor to fashion a memorial. They were not happy with the result. Basically, it's a rock with an embedded decoration that had no connection to art or his work, and you can still see that right by the front steps at Randall.
So Jens volunteered to try and make something more suitable. He fashioned a bronze memorial in the department's metal shop that symbolized the most important elements of Rich's research. The short, rich life of positronium was installed in 1996 in the courtyard south of Randall. It is a stunning piece and has appeared on the cover of the LS&A magazine. The Rich family was pleased. In fact, Art's daughters have small tattoos of the short, rich life of positronium.
Jens was inspired by the concept of memorial sculptures representing important scientific research, and in the last 30 years of his life, he devoted many hours, many days, fashioning beautiful representational sculptures with the help of his friends in the machine shop and former graduate student David Crosby.
He not only has some half dozen sculptures installed at various places around campus, but also at MIT, Stanford, the University of Nevada, Fisk University, East Carolina University, and the National Autonomous University of Mexico in Mexico City. Some of them we understand, some of them we do not.
We appreciate all of them. His maquettes are all over our house and in our yards, as well as the most spare ledges in the house on Dorset Road where our mother still lives.
Jens never made a sculpture symbolizing his own work, or for that matter, the work of his father, who is still well known in mathematics circles as the man behind Zorn's lemma.
Yesterday, when going through Dad's old digital files, I found a death plan for himself that he wrote in 1999. He was a bit younger than I am today. One of his final wishes, though 27 years premature, was this, and I quote, "I hope that my university colleagues will arrange a memorial session of a sort that would recall my research and teaching in physics, my work in the broader university setting, and my engagement with the arts. Thank you all again for making this wish possible. And with that, we will sit down and yield to the experts." Thank you.
Hi, can you hear me? Good? Yeah, so my name is Wolfgang Lorenzon. I've been here for 30 years. And I've been doing physics in nuclear physics and cosmology. I'm going to talk about, let's see, does it come up? Yes. Next one? Oh, next one. I'm going to talk about a sculpture that you can see here that Jens made. It's called spin-orbit coupling. Jens was an artist at many levels. I mean, he made lots of sculptures, and you're going to hear about 6 today. The one spin-orbit coupling you see up there, he made another one. I'm not going to talk about it. He also did book cover designs for a book about the history of physics here at Michigan, and book covers for famous introductory physics courses in electrodynamics. And he made pictures. We just heard before he made pictures, and very successfully. He found his wife. I've seen pictures of him, and the dearest picture I have is this, about 20 years ago, about my son. He was 8 years old, and he was here at Saturday Morning Physics, and Jens was, and I was talking about something, and then Jens stood aside and took this picture, and I still wonder what's going on in his mind. But let me start with the science of the art. Let me start with the Bohr model. As you can see here, the Bohr model was invented over 100 years ago. Depicts the atom as a small positively charged nucleus, which is surrounded by electrons, which travel on circular orbits, very similar to the planets around the sun. Except in this case, the attraction is given by the electrostatic forces, not by gravity. Now, this helped to explain the spectral lines that you can see in excited atoms by giving us the energy levels. But soon it was realized this is not enough. And he had to go on and use quantum mechanics instead of just classical physics. And that meant we had to replace orbits from planets with wave functions. And what you see here is just 3 of these wave functions, and which give rise to sublevels, and they are characterized by a new quantum number. It's called orbital angular momentum. And you can see they're different for different orbital angular momentum. They can get quite complicated. And you think that's already complicated. It was not enough. Then we had to introduce quantum mechanics and also spin. And you're probably going to hear today about spin was invented or postulated here at Michigan in 1925. And so Dirac, a very smart guy, took this all, put it together, and put this complicated formula up. And with everything green here, you should pay attention to. It's the total angular momentum. So it's the orbital angular momentum we've seen before on the previous page, plus the spin. If you put it together in the right way, you're going to get this fine structure splitting. Mainly, you get the splitting between the 2p 3/2 and 2p 1/2 you see up there. Now, what is spin? Spin is an interesting beast. It has no classical analog. It's purely in quantum mechanics. It is kind of an angular momentum. It comes in discrete values, half. Usually we leave away h bar, but h bar says it's an angular momentum, 0, 1. It determines how particles move. And it turns out that spin, in a way, behaves like a tiny bar magnet. And it depends what kind of particle you are. If you're an elementary particle with spin 1/2, you're a fermion. If you're one that has spin 1, you're a boson, and you behave completely differently. For instance, if an electron didn't have spin 1/2, something else, periodic table would look completely different, chemistry would be different, life would be different. Now, spin is very weird. If you want to get back in the same state in the spin, you have to rotate by 360 degrees, 720 degrees, not 360. So, in a way, like this plate, if you look at the green, as I go around here, and it looks to you, but certainly I'm not in the same state I was before. I have to go one more time, and now I'm back to the same state. Now, quantum mechanics, the weird thing is, this doesn't happen in quantum mechanics. It's just an illustration. There's no rotation in space. It's just a property of the wave function. And spin is very important. If you ever have taken an MRI, here's a slide through a head of a pig of an MRI. If you're interested in quantum computing, it's important. And spin can have actually quite a big effect. If you take the hydrogen atom, you have an electron and a proton. They are anti-aligned. And then you change the spin of one of them. They're aligned. The mass changes by a tiny bit. Let's say the mass of the proton is 1 in some units. You have to add 13 zeros plus a small number to see the difference. However, if you were to do that in the proton itself, where you have 2 quarks, they're aligned and one anti-aligned, and you take the one that's anti-aligned and align it, it has a 30% effect on the mass. And if you think about this small quantum mechanical thing can have such a big effect. This is mind-blowing. Now, in order to understand the effect, we have to do one more thing. We have to go to reference frames. And that really depends on the point of view. And I want to give you a little thought experiment, and I'm going to show you a demo. For instance, let's go in a windless day. You're going to stand outside, put your hand up, feel nothing. Now you go in the car, and you drive at constant speed. The same place, you put your arm out. You certainly can feel, most of you have probably done that, put your arm out and you feel the wind. Now, you say, oh, well, maybe things have changed. So on the phone with your friend, and how is it out there? You say, oh, I don't feel anything. Now imagine you're a proton, and the air outside are electrons, and now you're going to move. The proton is going to move at a certain speed. You have moving electrons, that means you have a current. And that's going to be important for the next slide. Now, there you may have noticed I changed the reference frame from being stationary or being moving. And I can do that here, now going from a linear motion into circular motion. I want to show you that, I'm going to wait a second until I speak. You're going to hear a tone. And if you're in the same reference system, if I change the reference system, I cannot spin you around, so I have to spin this thing around here. See if I can get this. Oh, this works. And now you hear it, and now I go around. You probably hear the difference. You hear a little change, right? And now if I bring it back, it's the same. So the sound hadn't changed. It's just a reference system. And that's what I say up there. If you change the reference system, things may appear quite differently than before. So now I think we're ready to understand what's going on. Let's go back to the hydrogen atom. You have the proton in the center, the electron on the outside. We learn in introductory electrodynamics that if you have a proton, a positive charge, you have an electric field, and the electron going around feels that field. Now the electron that's important, is going almost at the speed of light, because the uncertainty principle tells us if you're that's short, and that your space is so well defined, your momentum has to be big, and so it basically goes to the speed of light. Now let's put ourselves on the electron. If you're on the electron, what do you see? Like on the merry-go-round, right? Suddenly things go around you, and so the proton goes around you. And what you just learned on the previous slide, if the proton goes around you, there's a charge going around, you have a current. And we also learned that if you have a current, you have a magnetic field. So the electron feels a magnetic field at the position where it is from the proton going around. And now what happens physically, the magnetic moment that's associated with the spin interacts with the magnetic moment, with the magnetic field, which comes from the angular momentum. And there you have your spin-orbit interaction, and which leads to splitting of lines. And now I need to go to the next slide. And since we talked about the hydrogen atom, what happens? You would get a red line at 656 nanometers, which splits. Now the apparatus we have here is not good enough to see this. 1/6 of a nanometer. So you have to go through a heavy, oh, what happened?
Oh, that was me.
Huh?
That was me.
Was you?
Yeah. Are you going to?
Yeah, oh, we can see it on the side. Oh, I see. So we're gonna go here to sodium, the sodium lamp. Sodium is heavier than hydrogen, while the splitting is bigger. And what you can see is, you can see a line at 591, which is split. This is the spin-orbit coupling. That's the splitting due to spin-orbit coupling. So that's the science behind the sculpture. You ready?
I'm Roy Clark. I'm an applied physicist. I do a lot of work in condensed matter physics, and I'm also a spectroscopist. Jens and I go back a long way. In my 45 years career at the U of M, Jens was a mentor and an inspiration to me the whole time. And when it came time to install his last and magnificent sculpture, this was the last one that he did, I stepped up and organized the university's process for approval of that installation, and also two memorial occasions, one of them at Fisk University, the alma mater of the graduate alumnus, Elmer Imes, that this science is related to. So I was very proud to do that. And I was also pleased that the Ann Arbor Observer, those of you in the local community, know this, that they have a competition called I Spy. And this was the object of interest for February of this year. And I pointed out during the update here that this was a wonderful, commemorating a wonderful trailblazing discovery. And in the next few minutes, I'm going to explain why that was so important. I want to acknowledge here the contribution of pointer. David Crosby is also an alumnus of the university. He was the machinist that helped Jens to produce this magnificent work of art. And David Crosby is a long-time collaborator and a brilliant machinist that was able to put this together. He actually put two of these together, one of them at the campus of Fisk University in Nashville, Tennessee, where Elmer Imes did his undergraduate work. A brief bio of Elmer Imes, a very interesting character and as you can see, a very intense portrait here with a penetrating gaze. The background here is one of the spectra that he measured here at the U of M to establish the evidence for quantum mechanics applied to molecules. And he started his studies around 1915 here at the U of M. He got his PhD with Harrison Randall. There's a portrait of Randall holding a dispersion device called a prism. We'll come to that a little bit later. He was the second Black American to earn a PhD in physics, and actually the first to publish his work in an international journal in 1919. So this pioneering work has gained very much international acclaim over the years. It has many applications. I'll mention some of them later. After graduating from the U of M, Elmer was active in the Harlem Renaissance movement in New York City. And in 1929, he returned to his alma mater and elevated the status of the physics department there, which was chaired later by several graduates of the U of M graduate program in physics, and they established together a distinguished center in infrared spectroscopy. So all of the action here is really in the infrared region, which is where this spectrum is established. So the period when Elmer Imes did his main work, which was around 1913 to 1918, was a period of intense and exciting work in the field of physics, namely the beginnings of the quantum theory, starting with Max Planck's Max Planck was establishing the principle of the quantization of energy in 1900, followed by Einstein's quantization of vibrational modes of motion. So energy that goes into vibration is a quantization process. During this time, his advisor, Harrison Randall, did something very bold and very significant. He went on sabbatical to Germany, where all of this exciting work was going on. He learned about the beginnings of quantum mechanics. He was involved in the work of Friedrich Paschen, who, after whom one of the series, the infrared series, of course, was named in his honor. And he learned about the importance of infrared spectroscopy in the process. He came back to Ann Arbor charged with this excitement that he'd learned about and essentially brought quantum mechanics to the United States in the second decade of the 20th century. Now, Wolfgang's presentation emphasized the role of angular momentum, and that can be quantized. He talked about it in terms of the orbital nature of electrons in the hydrogen atom. I don't need to go through that. So it was thought at the time that maybe these ideas of quantization of things which rotate, like electrons in this Bohr model here, maybe those ideas can be transferred over to molecules. Molecules have additional degrees of freedom. We think of them very often as two atoms connected by a force. We now recognize that this object can have degrees of freedom, which can hold energy and have energy states. The rotation of the molecule is one. There are several 2 degrees of freedom that are important for rotation. There's also a vibrational, instead of a rigid rod. Another model of that is to have the 2 atoms connected by a spring-like force, and that can also be quantized, as Einstein showed in 1906. So these degrees of freedom were covered theoretically, but hadn't yet been established by experiment. And as you all know, the goal of physics is to take theoretical ideas and do very careful, precise experiments to see if those ideas match with experimental reality, and that's exactly what Elmer Imes did when he did his thesis work at the U of M with Harrison Randall. What a perfect combination of minds and circumstances and zeitgeist that occurred at that time, and that's what this rotation is quantized last work of Jens Zorn represents. There's an experimental genius behind those measurements, and Elmer Imes was charged with designing and building a spectrometer that could do those very precise measurements. And what was achieved here with this design, which incorporated something really new at the time, which is the diffraction grating combination with a traditional salt prism to isolate the region of interest in the infrared that was of interest for looking for molecular signatures of rotation, quantized rotation. So this device had the highest spectral resolving power of its time, something like 20,000 resolving power. It relied on that resolving power, relied on the world-leading quality of Randall's diffraction gratings. I actually have the original diffraction grating that Randall produced in his lab. This what I'm going to show you is the actual diffraction grating that was used for these experiments right here on the table. And I'll show you that what is meant by, if you just hold this steady here. So I'm reflecting a laser of single wavelength off the surface of this diffraction grating, and you'll see a series of dots, and those are the orders of diffraction, and the spacing between them tells us what the wavelength of the laser is as a result of interference, constructive interference of waves. So that diffraction grating in 1915 was state-of-the-art. It's still very impressive and still in good condition, as you can see. And that really was at the heart of the genius of this design. Now, the results that came out of this are truly spectacular. First of all, the results established in this green highlighted section here that they provided support, experimental support for a region of spectral analysis which hadn't previously been explored, and supported the recent theories of Sommerfeld and others and Bjorn that suggested quantization of the rotational degrees of freedom as formalized here in this energy expression, which here's the quantum number of rotation, angular momentum, J, which Wolfgang mentioned in the atomic context. This is now in the relationship of a diatomic molecule with a moment of inertia I. And it's significant that I is on the bottom here. So a very small I requires very high energies to excite. And they're very difficult to look for and measure accurately. Imes was able to do this. If you look at his spectrum, this is essentially wavelength versus absorption. And a peak here means that energy is being absorbed by the molecule. Each peak in this diagram is an absorption at a certain wavelength or energy. And if you look carefully in this circle where I've highlighted, there's a splitting. And that splitting is the key to proving that this equation, which says that rotation is quantized, fits the quantum number distribution of energy levels associated with that quantization. These are very weak, as you can see, very weak signals, and those were measured very accurately and shown to correspond and support the existing theory back in the very early days of quantum mechanics. It's also significant that this work, like I said, was the first work in an international journal from a black scientist in the astrophysical journal. Some of you may wonder, why astrophysics? Well, I don't know whether Imes knew this at the time, but that has become a very important branch of physics, of astronomy and astrophysics in the last few years. Let me mention that a little bit later. Oh, also, let me just point out one other thing. Einstein's prediction of vibrational mods here predicts that you should have an equally spaced set of levels due to the vibration, and those can be seen on this equally spaced peaks here in energy. This is in wavelength, so here's the vibrational aspects, and these small splittings are due to the rotational contribution. Okay, so the significance and impact of this work stretches far and wide, and over 100 years, and is still highly relevant, especially in the field of biological research, biochemistry, biophysics, and also clinical practice. And I want to mention that roughly 50 years after Elmer Imes got his degree. Willie Hobbs Moore also got her doctoral dissertation defended at the U of M working with Sam Krim in 1972. And she was the first black American woman, to earn a PhD in physics here at the U of M. So there's a kind of progression of interest in this field, which has grown and grown and grown. And Elmer Imes was the one who really started this in the experimental field. Finally, bringing us up to date, 104 years after Elmer Imes did his work, the James Webb Telescope was launched into deep space, and its special characteristic and abilities were to combine imaging of a telescope that normally has those capabilities with the capability to do spectroscopy. And in particular, spectroscopy in the infrared, where Elmer Imes focused his work. And this is a kind of like what Elmer Imes did. You have a star emitting light through the atmosphere of a planet, which passes in front of the, between us and the star. And as that light passes through the atmosphere of what is called an exoplanet from another solar system, the absorption features, in this case water molecules, can be detected as absorption peaks. So you can actually study the chemical composition of exoplanet atmospheres, and you can look for biological signatures in the infrared, which is a field that's now called astrobiology. And now this telescope, which is one of the most impressive instruments that science is able to work with now, can give us these wonderful images. It's the Cartwheel Galaxy imaged in the mid-infrared region, and all these gas energy levels, gas-like energy levels show up in very spectacular detail. And this gives us a new window on the universe and astrophysical processes. And with that, I just want to mention one last thing. I need to warm up my coffee. And it's okay, I got it. That should do it. So this was a demo. And that's better. So the microwave, you can thank the work of Elmer Imes, because the rotation of the molecules in the water and the coffee have friction with the liquid, and that spectral property of quantization allows that energy at a certain frequency to oscillate the rotational mode of the molecules and put heat into that and warm them up. So that's what we do. That's the physics we use when we put something in a microwave. Thank you very much.
Good morning, everyone. My name is Tim McKay, and I am a professor of physics, astronomy, and education here at the university. I had the great good fortune to arrive in 1995, just as Jens was beginning his artistic career. I remember the episode of the short, rich life of positronium very clearly, in part because the first paper I had written as an undergraduate involved positronium. And I arrived on campus, and they built this first sculpture, which we all went and looked at and thought, that's not a very good sculpture. And a year later, Jens produced this really magnificent sculpture, which I have since, in the last 31 years, used to teach people about positronium, I don't know, hundreds of times. You can't walk by it and not want to stop and explain it to people. It's such a great example. Jens was also, of course, a fantastic example of the ways in which art can illuminate science and can make it accessible to many more people. So when I was working as the director of the LS&A Honors Program, I asked Jens to make a new sculpture to particularly commemorate a discovery made by an undergraduate student. And that discovery was the invention of fiber optics. So in 2011, we commissioned Jens to make a sculpture that would commemorate the work done by Lawrence Curtis, the invention of cladded optical fibers, which he did as part of a project with physics faculty members while he was an undergraduate. They were working to build a gastroenteroscope, a tube you could put down your throat into your stomach so that doctors could see what was happening inside your stomach without actually cutting it open. Kind of a good thing to be able to do that. That invention was an enormous watershed in the creation of the fiber optics industry. And so I want to tell you just a little bit about that story and about the way in which this art is used to commemorate not only Lawrence Curtis's work, but the work of all undergraduate researchers at the University of Michigan. So this is the sculpture, and it now hangs in West Hall 335. This one's not outside, it's in the building. And what you can see in it is a set of kind of channels made of aluminum with copper pipes that oscillate through those channels. The copper is kind of trapped in those channels. It's directed by them along this set of fibers. That is the visual image that Jens put together in order to explain how fiber optics work. So let's talk about the physics of fiber optics a little bit. How is it that you trap light inside a fiber? Well, light shines through many transparent materials, as you know, things like air and water and certain kinds of glasses and so on. When light travels from one material to another, let's say from air to water, or from water to air, the way it crosses that boundary depends on the properties of those two materials. And there are two things that can happen. When it goes from one material to another, it can bounce off, it can reflect, or it can transmit through from one to the other. And if it does that, when the properties of these two materials are different, it will change direction. So physicists would call the first one reflecting, not a surprise. And we would call the second one, where light changes direction, we would call that refracting. That's a little more obscure, but it's just changing direction, okay? So let me show you a demonstration of some of this. So what we have here is some light that will come out of this slide projector. Remember slide projectors? They still are nice sources of light. And the light that comes out of this is bouncing off a mirror right here, and then off another mirror at the bottom. And I can change the direction of this light beam that is going in water. You can see it right now going in water, striking the interface with the air, right, there's the air above and water below, and reflecting off. If I turn it a little higher, you will see that the light can actually pass through from water into air and change direction. Right? So that's the refraction part. Turns out, if we make this angle steep enough in the transition from water to air, then it will all be reflected. It's totally internally reflected. It stays inside, all right? So how can you trap light in a fiber? If you send it down the fiber and it totally internally reflects every time it hits the wall of the fiber, then it stays in the fiber, right? Okay? So that's the basic principle behind fiber optics and how they work. Seems simple enough. So what is the thing that Curtis did? Well, it turns out if you have fibers made out of glass like this, they do direct the light from this flashlight through the fibers. But you might notice that there's also light leaking out the sides of these fibers. It doesn't stay in very perfectly, right? So that's a problem, because if you want to make fibers that are long enough to carry light down into your stomach and back, for example, or across the ocean, the way we do now, they have to keep the light in and not let any of it out, all right? So what Curtis did in order to figure out a way to keep the light inside the fiber was to make what are called cladded optical fibers. So to handle the losses that normally would happen, in this picture you can see if light bounces off in that fiber multiple times, and if every time it bounces off you lose some light, then by the time it bounces 10 or 20 times, you've lost almost all the light, right? So what he did was to make cladded optical fibers with one kind of glass on the outside and another kind of glass on the inside. So the light never actually reaches the outer surface of the glass fiber. It bounces inside. It's contained inside. Why is it so important to avoid the surface? Well, surfaces can get damaged super easily, right? If you touch them in any way, they can get damaged. So by keeping the surface inside this fiber, he solved the problem of light loss and made the fiber optic industry possible. Let me tell you the story about how he did it, because it's a pretty great story. Curtis discovered these light losses from bare fibers very quickly when he was hired as an undergraduate to work on this project with some physics faculty. And he talked to the physics faculty about it. In fact, the famous story is that he visited them when they were playing bridge during lunch and asked them about it, right? And they all said, I don't know, why don't you try putting some lacquer on the outside? And so he went off and tried that. He spent a summer trying putting lacquer on the outside of fibers, all different kinds of lacquer, didn't work. But he had another idea. He thought maybe wrapping one glass around another kind of glass would enable this to work. And here's his own description of it. This is from Jeff Heck's book called City of Light. It's a history of fiber optics. The poor results with lacquer left Curtis itching to try making a fiber from a glass tube collapsed on a glass rod. Take a glass tube, put another glass through it, melt it all together, and stretch it out. So that's what he did. He finally got a chance on December 8th, 1956, when the professors were away at a conference, right? They didn't want him doing this, so he just did it on his own. In the basement across the street here. He bought tubes of a soft glass with a refractive index lower than the Corning rods, then put a rod in the middle and a tube around the outside, melted them all in a furnace, and started dragging it out into a fiber. Here's the story of what he says. It was probably the most exciting day of my life, he recalls. He walked down the hall. So he had it in a furnace. He grabbed the end of this and started pulling it down the hall away from the furnace. And the light from the furnace was shining through the fiber. And that light stayed bright. He got down to the end of the hall and it was still bright, right? So I could see the glow from the furnace and I knew it was good. His glass-clad fiber transmitted light far better than any optical fiber ever made. The college junior had broken through his professor's conceptual logjam. In part, Curtis was lucky, the book says, as he readily admits today. But his was the luck that comes from the intelligent and the observant. He had been trained to really be careful and thoughtful about it. That's what we do when we do research with undergraduates, is we give them that kind of training to be ready to make the discoveries that they should make. Now, of course, modern fiber optic cables are incredibly complex technologically. It's a fascinating industry and an enormous industry. Curtis ultimately won the patent for the invention of cladded optical fibers, but it was so important that they fought that patent from 1956 to 1971 before he was finally awarded the patent. So Curtis, one of tens of thousands of undergraduate researchers, there's a picture of him here, with some of the apparatus that they used. Undergraduate researchers have always worked with physics faculty, often making important contributions. His first invention, he made many other inventions in his life, was a great example of this. And we should all remember the enormous impact that undergraduate researchers have on the research that's done here, both the way we train them to become researchers later in life and the actual contributions they make to research. And Larry is a great example of that. What it's all about, doing research, is about making them intelligent and observant and ready to be lucky, because that's what you have to be. All right, thank you very much. There you go.
Thanks. I'm Steve Cundiff. I am a professor in physics. I do ultrafast optics. I've only been here on the faculty for 10 years, although I've actually known Jens for nearly 40 as I was a graduate student here. And when I was beginning, I believe he was busy actually doing what Tim is doing now, being associate dean, and he invited me and some others from my group to actually use his lab. So I got the pleasure of actually using his lab in Randall. So I want to talk about the concept of optical harmonic generation or second harmonic generation. This is an image of the concept that Jens was inspired to design based on this. He actually never made the one on the top. And there is not a permanent one. There was a temporary installation out here in this part of what used to be East University that you can see here. I don't actually know how long it was there for. So what is second harmonic generation? It is a process that happens when you expose material to very high light intensities. And so it was something that couldn't happen until there was a source of high light intensity, and that source is the laser. So a key thing was the demonstration in 1960 of the Ruby laser by Ted Maiman at Hughes Research Labs in Malibu, California. So that's a picture of Maiman there with his laser in front of him. There's a diagram up here on the top right of the laser. It's actually quite simple. In the center, labeled G there, is a small ruby rod. That ruby rod has two polished ends, one slightly curved. They deposited silver on that to make mirrors. The spiral thing you see is a flash lamp. So those of you old enough to remember old copiers, they would have a long tube that would illuminate and scan across it. So that is also the same thing. They basically took that, made a helix out of it. They run a burst of electrical current through it. There's a gas in there. That emits light, which then excites the chromium atoms in the ruby. That light bounces back and forth between those two mirrors, and it gets amplified every time it gets through by the process of stimulated emission. That's what the S and E stand for in laser. And then it comes out as that bright beam to the left. What's remarkable, as I said, this was demonstrated by Maiman in 1960. And Peter Franken here at Michigan realized, hey, here's an opportunity to do something completely new. What happens if we can expose the right material to this high intensity light and see if we can change the frequency of the light? Not just filter it, but literally change it, okay? So this was the experiment, quite simple. Again, the ruby laser on the left, a focusing lens, a piece of quartz. That quartz is what underwent the harmonic generation. Another pair of lenses around a prism. We just heard about prisms that diffract the light. So just as Newton used a prism to separate the colors of the sun, here Franken and coworkers were using it to separate the 6943 angstrom light from the ruby from twice its frequency or half its wavelength. Now it's interesting if we look at the authors on this. So Peter Franken was a professor here at Michigan. Albert Hill was his grad student. I actually saw a presentation by Albert Hill on this in 2011, so 50 years after this paper. I have to say, as a modern laser physicist, I was amazed because he explained that this ruby rod with the silver mirrors would only last for maybe 10 to 20 shots before the mirrors were damaged. And they had maybe 3 or 4 of these rods, so they would pull the rod out, they'd ship it out, it would get polished and recoated, and then they'd have to put it back in. So his PhD thesis probably had maybe 200 laser shots in it, whereas today we use lasers that make, literally 100 million laser shots in a second. So Wilbur Peters, the third author, I believe was a postdoc. But what's interesting is the last person, Gabriel Weinreich, was also a professor here who did not do optics, he did acoustics. And apparently he is the person who told Franken and coworkers, don't use glass, because originally they just put a piece of glass in there thinking, oh, we just have to hit it hard enough for this to happen. Use quartz. And so that understanding why we need quartz also explains the whole process. So what we can think of is the quartz, which is SiO2. That's the crystal structure of it you see up there on the left. The red are the oxygen atoms, and the gray are the silicon atoms. What happens is the laser drives the electrons, which are in those little covalent bonds between the atoms, and it makes them go back and forth. And physically, that's no different. You can think of those electrons as being connected to the atoms by springs. And so the laser is this oscillating motion that's driving that electron. And the key thing is that independent of the frequency that we drive it, the motion of the electron is always, well, actually we're hitting funny resonance there, it's always sinusoidal at the same frequency as the drive. The amplitude will change, okay, but we always get sinusoidal motion, okay? And so in a spring, the force that puts on the electron, if you will, is proportional to the displacement, and that means that actually the energy, the potential energy, is proportional to the displacement squared. So you can think of this actually in another mechanical analogy. Let's say you had a parabolic bowl, and you had a ball sitting on the bottom of that, and we had a, let's see if I can get, all right, so anyway. We have a ball that's sitting back here, and we give it a sinusoidal drive, so you can think of just tilting that bowl back and forth. It will make oscillatory motion in between, as shown on the right here. This is the oscillatory motion. And as long as this bowl is perfectly parabolic, that means that the motion will be perfectly sinusoidal. But what happens if we don't have a perfect spring? What happens if that spring gets a little softer as the ball gets farther away, okay, from the center point, or in this case, it gets higher up in the potential? What will happen is the energy won't go up quite as quickly, and now when the ball moves up here to this edge here, it will actually go out a little bit further, okay? And the same thing will happen over here. So if we look at that, what will happen is the blue line we see here is the perfect parabola, the perfect spring, whereas the orange line is going a little bit further in each direction because that spring is softening, so it can go a little further. And we can actually show that that corresponds to the summation of two sine waves shown here. Now the key thing is the green sine wave, which is the additional one, its peaks have to anti-align, or they have to be flipped because they have to align. So in other words, we need to go 1.5 cycles in the time that the original one goes a half a cycle. So that means this frequency has to be 3 times the frequency of the drive. Now, this is not what happens in quartz, because you have 2 different atoms. You have what's called broken inversion symmetry, that when the electron goes one direction, it senses one atom. When it goes the other direction, it senses the other. So now the potential or energy, the bowl won't be symmetric, but rather it will go higher on one side and lower on the other, okay? And now if we think about the motion, it's going to go further in one side, that's the oranges here, but actually not as far, because we drive it up, it's going to go out farther over here, but over here it's going to go not as far. And when you look at that motion, you can then make that in terms of 2 sine waves, but this second sine wave is at twice the frequency, because here it adds, whereas here it actually has the opposite sign, so it subtracts from the motion here. So this was the key thing that Franken pointed out, was that you needed this situation where you have this difference in the 2 directions for the springs that are basically holding the electron in place. And the key reason this was important is because they only wanted to try to see this second harmonic, the frequency being twice, the wavelength being half, because if you could, in principle, if you drive it hard enough, you would see that third frequency, the third harmonic, but it's a weaker effect. So I just want to finish by saying there's actually an amusing anecdote about this. So this result was published, as I show at the top here, in Physical Review Letters in 1961. And as you can see here, it says they're photographic plate. So the actual results that they sent to the journal was the photographic plate. Now, I say that to students these days, and they're like, well, what? You know? What's a photographic plate? Because they've actually never used a film camera, right? So it's basically a piece of film. And that film would get highly exposed. And so this is actually an image from the journal. So that black splotch on the right is the ruby laser highly exposing that film. And the blue light was very, very weak. So over on the left is where the blue light was. Now the thing is, and that arrow points to where the blue light exposed the film. You all see it? Yeah, no, you don't see it. Well, what happened is the copy editor at the journal, Phys Review Letters, said, oh, there's a little piece of dust on your photographic film. And they airbrushed it away. So this paper, which is the first demonstration of second harmonic duration, it's the first generation of a broad field called nonlinear optics, actually doesn't have the result in it, okay? And I have to say, if you're worried that maybe they made it up or something, don't worry. I have seen the film. There was another former faculty member, John Ward, who had it, and I believe it is actually in the U of M archives to show that the result was real, even though it had not been reproduced in Physical Review Letters. Okay, so thank you.
Good morning.
Good morning.
So my name is Henriette Elbang. I'm a theoretical physicist here at U of M. And today I will talk about this sculpture you see up here, which you can also go over afterwards and see in the courtyard between Randall and West Hall. It is Jens Zorn's sculpture called Veltman's diagram. So this commemorates the Nobel Prize from 1999 awarded to Tini Veltman and his former student Tuft. And in the words of the Nobel Prize Committee, it is for elucidating the quantum structure of the electroweak interactions in physics, work that was done in the 70s at the University of Utrecht. But later, Tini actually moved to Michigan, where he was a faculty member from 1981 to 1996 when he retired. So when I look at this, I don't know what you see when you look at this sculpture, but I know what I see because I'm a little bit environmentally damaged from my field. And what I see are two particles coming in on the left, and they scatter and do something with each other, and then there are two particles that come out on the right. So obvious to me, this is a Feynman diagram, but of course I also see Feynman diagrams just about everywhere I go. So in Jens Zorn's words about the sculpture from the website, it says that this is a sculpture in which the diagonal arms call to mind the incoming and outgoing particles, just like we talked about. The square structure at the center represents the exchange processes between particles. And the curved steel arch up here in the right corner of this square, that derives to Veltman's innovative method of calculating particle interactions. So let's talk a little bit about particle interactions. So what is it that particles do, and what is it that particle physicists do? So particle physicists often study what everything in nature is made of by doing scattering experiments. That means that they take particles and they smash them together. And so I will show you with my own hands how this works. I will risk my own health for you. But as always with good experiments, you need safety equipment. Otherwise, you're not allowed to do it. And so I got a big safety goggle here. Let's see if we can make it fit. There we go. All right, so you have to help me with a little countdown here. Are you ready? 5, 4, 3, 2, 1. Whoa! Are you all safe there in the front? I wasn't allowed to do it close to you. So just like the Legos spread everywhere here, just like they do at my house every day, the particles in big particle accelerator experiments smash together, and out comes new sprays of particles, just like at the Atlas experiment you see in this colorful photo here. And what we do what experimentalists do is that they build giant detectors to pick up the energy, and they track the particles and to figure out what happened, and from that we learn about fundamental building blocks of nature. What theorists must do is figure out how to calculate these processes. And Feynman in the 50s started telling us how to do this, and these are called Feynman diagrams. And what it does is that we have something that is small, some small coupling. We do perturbation theory in it. Loosely speaking, the leading order terms in this scattering process is captured by diagrams that don't have any loops in them. So they're called tree diagrams. And each of these diagrams translate into some mathematical expression, and then you have to add them all up. Now, when you have to then, this is not just classical physics, you also have to put on your quantum hat once in a while and compute the 1 loop and 2 loop corrections and 3 loop corrections, depending on to which precision you need your result. And in physics, we need quite high precisions because our experimentalist friends are so good at what they do that we need to, and we'll hear more about it in the next talk, how good they are at it, we need to calculate to high loop orders. So let's see some examples of diagrams. Here's a 3-point interaction, a 3-particle interactions, and you use that to build up all the diagrams, and each diagram translates into a mathematical expression. On the top, I gave you a 4-point example of 4 particle. Here's 2 particles coming in, 3 out. There's in the second line here, 2 particles going in. You can think of it as 4 particles going out. And we need all those processes to understand it. We can also draw the building blocks in a different way. Here's 1 particle decaying to 2 others. Or the reverse process is 2 coming in, annihilating to 1 and coming out. And then you can keep going. And at some point, you could have like 64 particles participating. And you know how physicists like to call these things funny names? You can call them like Akron or Michigan State or that place down south. And all of a sudden, you have a championship. So Feynman diagrams are incredibly useful in many contexts, as you can see. They're useful not just for March Madness brackets, but they're also very useful in condensed matter physics and particle physics to organize our calculations. There's just a little catch. And that is that when we translate them into mathematical expressions, there's a rule that says that every time you have a closed loop, every time you do your quantum, you have to integrate over that particle's momentum that runs in here, its momentum and energy, and that could be arbitrarily large. That means that you're doing some integral from, say, minus infinity to infinity, and sometimes those integrals give infinity. But you don't go out in nature and measure infinity. That never happens. What you see in nature is always a number when you measure something, and so what do? I mean, you could trash the whole theory, but thankfully, Veldman and 't Hooft were a lot smarter than that, and they devised a method to handle the infinities that come out of these diagrams systematically. And they showed that this can always be done to make sense of the predictions of the theory, and in fact in a very physical way. And that was in particular done for the weak interactions that they got the Nobel Prize for. This is what is said, that the theory is renormalizable, and that is incredibly important for what we call the standard model of particle physics today, for which these weak interactions are part of it. And that is what this statue commemorates, this sculpture commemorates. Now, there's another little problem with Feynman diagrams that we sort of need to talk about, is that once you have figured out how to handle the infinities, then you also have to face the fact that as you start writing down the diagrams, there are just so many of them. So here are 9 diagrams. There are just some subset of diagrams that are needed to calculate an electron coming in and a positron coming in. They annihilate, they do some stuff, and then they produce a Z boson and the Higgs particle. So there are so many diagrams. This is so hard to do. Even once you mastered all your infinities and renormalization and everything, every one of these diagrams is some huge mathematical expression, and then you have to add it to something else, and you have to simplify it, you have to do something with it. This was not done until in 2023 fully for this particular process. So Veldman realized that this was an issue, and he was like, well, there's so many diagrams, I need to calculate them. So he decided that he was going to design a computer algebra system that could do these simplifications for him. And this was initiated already around 1962-63. And I just want to remind you that computers back then were not exactly handheld. This was one of the machines, the first one he designed his code for, and you know, that had the memory of about 2 million times less than what my laptop has today. Now, by the time he released the initial documentation with this in '67, there was a huge upgrade. Now you had almost a megabyte of memory. And here are the little screens. And if you zoom in on them, you can sort of see names of physicists. So I hope they used it for better things than just their payroll. But at least there was also names of physicists in there. But it's very interesting. So Veldman kept developing this because every time there was new developments for computers, he wrote it as assembly code. So he had to rewrite the code. And so he wrote it directly for the new computers that came in. And he kept developing this also when he was at Michigan, all the way up to 91 when the last version was released. Here's from what he called his computer program. You may read it as schoonship, but then he would laugh and say it has to be pronounced in Dutch, and it's something like hoenhip. But people who are Dutch can correct me on that. But anyway, that was from the manual of hoenhip in 1975, where it says that this program deals with formulas rather than numbers. This is not a numerical code. This is something that symbolically manipulates expressions. And the problem must be formulated by specifying an expression followed by a set of substitutions or commands to be applied to it. So I see that there are some students in the audience, and so you might know that there's a program where you put in a mathematical expression, and then you write simplify. And that's exactly what this kind of thing did. It simplified expression according to the rules of the math in quantum field theory. That is a forerunner for something that we use today, namely Mathematica, that was built by Stephen Wolfram, who in fact, as part of the inspiration for building his first symbolic manipulation, used Veltman's code back in the 70s. And he started designing these kind of codes back in 79. And in 88, the first version of Mathematica was released. We use it now today in many different contexts. And of course, now there's new revolution coming from large language models that even help us optimize our Mathematica codes to make them run faster and better. So what's the moral of the story? The moral of the story is that good physicists pursue problems that intrigue them. They don't necessarily have to be something you can sell or something that makes your house better. But when these physicists pursue these problems, hard problems, like in this case, Veltman did, and he saw all these diagrams, and I need to do something about it. Physicists develop new technologies, new methods, new hardware, new software, some ways of solving the problem that their heart burns to solve. And so out of that, out of general relativity, we have gotten GPS. We have gotten the internet out of how CERN physicists needed to communicate and share data. And we have gotten microwaves and so on, and computers. And so the message that if you take something away from today, including to the legacy of Jens, is that fundamental science just rocks. Thank you.
Oops, got to go through your whole thing. Okay, well, hello again. I am physics professor Tim Chupp, and I am going to talk about this lovely, amazing sculpture that has been in the courtyard between Randall and West Hall and Neil. And it's called G-2, and that's the way Jens spelled it, as you can see at the bottom. And the question that's being addressed by this sculpture's experiment that it commemorates is how large is the intrinsic magnet of the electron? So you've seen some of this already in Wolfgang's talk, etc. The top picture here is called a spectrum, the rainbow, and the dark lines in that rainbow, it's a spectrometer that uses a diffraction grating, for example, that's looking at the sun, and because of the solar atmosphere has neutral atoms in it, there are some dark lines because that light is absorbed, and that's what those dark lines are. And in the very middle, which is also at the peak of our what we can see, our visual color sense, is what's called the D line, and that is from the atom sodium, and you can see that there's this little pair of those D lines, so we've seen that, okay? So this led, this and many other experimental results led to the proposition of electron spin in 1925. Last year was the 100th anniversary of that, and we actually celebrated that because two of the three people in this photograph, George Uhlenbeck and Sam Goudsschmidt, along with Heinrich Kramers, here shown in Ann Arbor. Uhlenbeck and Goudsschmidt were professors here. They came here in 1927. Shortly after, as graduate students, they made this contribution to our fundamental understanding and quantum mechanics. They said it was clear to us that we had to assume that two things: each electron not just orbited, as Bohr and others had shown beforehand, but were spinning like a planet rotating around its axis. And spin is a kind of angular momentum, but the thing about that is because of the nature, including the fact that there are two states, of experiment, the units had to be 1/2 of the unit, fundamental unit of angular momentum in quantum mechanics, which is this h bar, which we've seen. So physicists know that when it's quantum, there's an h bar. And we're very happy to have these hats that were provided by the Society of Physics students. The second is that each electron possesses a magnetic moment. It's a magnet. It has a north pole and a south pole, and that north pole and south pole is aligned with the axis of spin. Okay? So each electron is a magnet. And measuring the strength of that magnet has been an industry ever since. First in atoms, but then here at the University of Michigan, measuring directly electrons. So what physicists call the strength of the magnet is the magnetic moment. A moment is a way of characterizing something that's distributed, a distribution, so there are moments. And if you think about back to the orbiting electron, which is a charge, that makes an electric current, right? So there's a charge that's flowing, so that's an electric current, and that electric current can be related to the angular momentum of the electron, its momentum, and the radius of the orbit make the angular momentum, and angular momentum is quantized, we've heard that many times today, in units of h bar. And so if the calculation simply shows that the magnetic moment, that's what this mu, the Greek letter mu with an arrow over it, because it has a direction, it's a vector, is proportional to L, which is the angular momentum. So it should be quantized in units basically of h bar. But it turned out that the electron's moment was 2 times too large if its intrinsic angular momentum at spin is 1/2 h bar. That was explained by Dirac in this amazing paper, which also predicted antimatter, which is really fascinating as well. So it's quantum, which has an h bar, and it's relativity that he put together with quantum mechanics. And when we think about relativity, we think of c, the speed of light. So you can see there's a formula there that has both the h bar and the speed of light. Why? It turns out, however, that a number of experiments, as experiments became more and more precise, we realized that G was not exactly 2. Close, but not exactly 2. And it started emerging that it was about 0.1% different from 2, a little bit larger. And the reason is that as an electron exists, and the way we like to put it is propagates through space-time, so as it moves through space and time, it exchanges energy with the vacuum. You think of a vacuum as empty, but it's not. It's an infinite number of possibilities because of all the particles that exist, which can go into come into existence and go out of existence for very short periods of time. And this is essentially governed by Heisenberg's uncertainty principle. There's h bar again. Okay, so delta, the Greek letter delta E, is the amount of energy essentially being borrowed from the vacuum, and delta T is the short time, and the more energy, the shorter the time, the weaker the contribution. But nevertheless, this is a real calculation. Maybe Henrietta can explain it better than I can. All right, so here's the Feynman diagrams that describe that. Let me describe the one on the left, which is essentially Dirac. The squiggly line at the top represents a magnetic field because the magnetic moment of the electron or a particle needs to be measured by interacting with a magnetic field. And going from A to B is simply moving through space and time. Okay? However, and you saw diagrams like this in the Veltman presentation by Henrietta, there can be energy borrowed from the vacuum to have just an internal photon, or a photon, which is an electromagnetic quantum, electromagnetic energy emitted, and between A and the interaction with the magnetic field, and then reabsorbed, because you have to, in the end, conserve energy. So the process has to essentially be able to go back to where it was. And then that was actually calculated by Julian Schwinger. Schwinger and Feynman, who's there on the right, and Tominaga won the Nobel Prize for bringing this to physics, and in particular with the understanding of the electron and other experiments that had been measured. The one on the right is yet more complicated, but nevertheless, energy is being borrowed in a slightly different, but actually less influential way. There's at the top, 1 plus 0.00116. That number, by the way, if you want to remember, could be used as a password or something like that. Hint, hint. Or a password hint. All right. And then the next one is actually a little bit smaller because the 00116 is the quantity alpha. Alpha is just the strength of electromagnetism. E is the charge of the electron. It's about h bar, remember quantum mechanics, C, relativity, divided by 137. Okay. Physicists also remember 137. That's another password hint that we use. And then the next term, that number is much smaller than 1. So if you square it, it's even smaller, right? And Feynman's contribution included understanding this thing called vacuum polarization. Okay. Now, I have been working on measuring G-2 for the past 15 years of my career, not of the electron, but of the muon. I'll tell you about that at the very end. But when I give talks, a few a year about this and more a few years ago, I actually use this drawing that Jens had in his notebook that shows his ideas for this sculpture, which is shown on the right. And I added the cyclotron orbit. Okay, so the way that this is measured and what this sculpture on the right shows is the magnet, which are the vertical brass, copper-colored, yellowish things are components of the magnet that's needed to measure this magnetic property. And the spiral is the path of an electron through that magnet. And that is an orbit, even though it's moving through the apparatus, that's called the cyclotron motion. And that's just the charge times the magnetic field. That's what B is divided by the mass of the electron. So we have a demonstration here. I have to turn this one to 100, the first one. And what you see here, actually, we have to probably bring the lights down a little bit. Thank you, Carol. Okay, so on the right, you can see, I can make it a little bit weaker just to show you what I'm looking at. Okay, that's an electron beam that's coming out of what's on the right in your picture, but there's no magnetic field, or at least a very small magnetic field, and if it's the Earth's magnetic field, which is pointing parallel, which doesn't have an effect. But if I turn up the magnetic field, I make an orbit. Okay? And the glow, by the way, is because there's a little bit of glass inside, inside this glass tube, which is otherwise evacuated, and so the electrons going through that gas make it glow. That's why we can see it. Okay, so that's the cyclotron, thank you. That's the cyclotron orbit part of this. That's the top that's in blue. But the other thing is that the G, the magnetic moment, also interacts with the magnetic field, causing what's called precession. And precession is something you can all understand. It's as easy as riding a bicycle. That was my joke. All right. Usually people laugh when I tell them I just told a joke. Okay, so this is our riding a bicycle. Monica's going to help me spin this up. Thank you. It's a little hard to see, isn't it? Yeah, but okay, so now if you're thinking spinning a bicycle, there's a torque on the bicycle wheel because of gravity and the way it's balanced, and this motion like this is called precession. And the torque is the magnetic moment times the magnetic field, and the frequency of the precession depends on the magnetic field and the magnetic moment, and E over m, simply. So those are the two things we put together. If you divide one by the other, you see the magnetic field divides out. That was a brilliant realization. Oh, yes, that's my graphic. All right, so G-2 that was pioneered, the measuring of the electron G-2 here at Michigan by Dick Crane. So I'm not going to go into detail and explaining the apparatus, but what you can see where I have a picture of the sculpture is also a picture of the apparatus, which looks similar. That was measured with incredible precision. And in iterations since the mid-1950s, parts per million, which already sounds very precise, and then parts per billion. That was the PhD thesis of Dave Wilkinson. You may have heard of the Wilkinson Microwave Observatory, which is shown in the upper right, and the famous picture of the universe in microwaves, which is shown just below that. That was Wilkinson's career after he left graduate school. At the bottom is the very best measurement of G-2, which is actually parts per trillion, or even, I had to look this up, quadrillion. So my work, to finish up, has actually been measuring the magnetic moment of the muon. The muon is, we say, the heavier cousin or bigger brother of the electron. It's one of three elementary particles that we call leptons that are charged, that are, we think, give a complete picture of nature as far as we understand it. Muons are produced in cosmic rays when protons, in particular, hit the upper atmosphere. So, by the way, it's carbon-14. And it turns out that muons are more sensitive to what we call new physics, undiscovered physics that is needed, in fact, to explain the universe as we observe it. So the universe has more matter than antimatter. There's something called dark matter. There's also dark energy. We don't understand neutrino masses. And there's more that is not incorporated into what we call the standard model, the picture that we have that explains most things. So there's must be new physics, unobserved things, which would manifest itself as particles, probably heavy particles, and the muon is more sensitive because it is heavier than the electron. So here's the experiment at Fermilab that we completed last year, actually. There's a big magnet. That's what the blue thing in the middle is, called a muon storage ring. We need lots of muons, which Fermilab provides, a magnet and a signal. There's the signal again. Anyway, just to show you what this adventure has been for me and my approximately 200 collaborators in this experiment. On the right, the purple bar shows the history of these measurements, actually since the 1980s. And they're extremely consistent. If you know how to look this, there are several bars in blue, red, and purple. The left-right extent of those shows the experimental precision improving over time. At the bottom, by the way, you can see the 116, right? On the left is, in green, was the theory, standard model calculation, which until a few years ago existed in the green box at the left, which was always what we call in tension, disagreeing, and if it had stayed there, if the theory had stayed there, we would have had what is considered a discovery of new physics. But for some reason, which I can go into, but nevertheless, the theory changed significantly, and that was a result of being able to use computers, in fact, in a new way to calculate the very hardest of the Feynman diagrams. So, I want to thank you all for coming. The science of Jens Zorn's art, which we've talked about today, is also the genius with one S of Jens Zorn's art. I also wanted to note that Saturday Morning Physics is supported by these endowments, and of course, by you. And we thank you for coming, for supporting Saturday Morning Physics. It's been a great year, and we also thank you for your financial support. And so on behalf of everybody who's spoken today, including Eric and Karen, thank you so much for coming and joining us. And all the speakers, we want to thank you.